Hey folks, yesterday we talked about the inflammatory response and kind of how it starts to get activated. And when it gets activated by histamines, it causes redness, it causes the tissue to become hot, swelling, and also a feeling of pain. So you get this puffy red tissue that's hot to the touch that also kind of hurts. But we never got to the part of how does it activate and attract body defenses? And that's what we want to focus on today. Now, yesterday what we looked at was a streptococcus infection where the cells around it got damaged. They release histamines, and the histamines come over and attach to receptors on the cells of the tunica intima. Those cells shrink, generating gaps, and plasma leaks out, filling this area with fluid. That's going to generate swelling. The capillaries also get bigger, increasing blood flow, and that'll make the area red, and that's going to make the area hot. And then the histamines also activate pain receptors that send signals to the brain, and then you feel the sensation of pain and the tissue hurts. But today's question is, how do we attract defenses to get rid of these streptococcus bacteria in the first place? How do we activate the defenses to get rid of these invaders? All right, so first part of the story. These cells release histamines. And the histamine concentration is going to be highest up by the area of damage. But as we get farther and farther away from the area of damage, the concentration of histamines is going to drop. So there's one part of the problem, one part of the story. But how exactly do the histamines help? How do they help to attract defenders? Well, I want to talk about the defenders for just a second. Already in your skin, you have dendritic cells that are just hanging out. They're always there. And their job is to identify and find when there's an infection. We'll talk about those cells in a couple of minutes. But before we talk about the dendritic cells, I want to focus on the cells that are in your bloodstream, called white blood cells. Some of them are called neutrophils, the most numerous white blood cell. And some of them are monocytes. Less numerous, but these are the big cells. We talked about a few units ago that these were the big eaters. Well, how do they know where to go? How do they know I need to go to my hand and not my foot? Well, let's talk about that for a second. I don't know if you noticed, but there are these little green molecules on the surface of these endothelial cells of the tunica intima. And there are also these little blue molecules on the two white blood cells. They look like they stick. They do stick. And as a neutrophil is moving through a capillary, if it bumps into these behave like Velcro, and they attach to each other. The monocytes and the neutrophils, they don't just have two. They're actually coated in these. And as the monocyte's traveling through this capillary, it'll stick, and then like Velcro, you can kind of tear it apart, right? Well, it'll tear off, and then over on this side, it'll stick. And these neutrophils and monocytes, they're gonna spin, they're gonna roll along the surface of the blood vessel. We call this process where they roll on the inside surface of the blood vessel, we call it margination, because they end up rolling on the margins of the capillary. If I say, look, what I want you to do is write in the margins of your paper, and you're going to write on the outside edges. And what these molecules, I don't think I wrote down what they are. The green molecule's name, these green molecules, their name They're called P-selectins. And these P-selectins cause the blood cells to roll on the surface, on the margins, on the edges of the capillary. All right, great. So they're rolling along the margins of the capillary, but how do they know? How do they know to get out there? How do they know to go where there's an infection? Well, we got this trail of histamines, this trail of breadcrumbs. Think of them as breadcrumbs. And this concentration declining, it's an indicator there's a problem. So as the monocytes and as the neutrophils are rolling along, if they bump into histamines, like, oh, wait, there must be a problem nearby. And if they notice, if they get towards these gaps, there are now gaps in the capillary because it's leaky, they're going to try to get out. They're going to try to leave the capillary and go towards the histamines, towards the trail, the breadcrumb trail. And what they'll do, this is kind of cool, they actually will squeeze themselves down and they'll wiggle through the gap. So this neutrophil, it's going to find the gap, it's going to find it, and there's histamines, there must be an infection over there, and they'll squeeze themselves down and they'll kind of wiggle out of the capillary. We call this process where they wiggle out of the capillary we call it diapedesis. Diapedesis is when they wiggle out. And the monocytes are going to do it too. And then they start traveling towards the bacterial infection, towards the concentration of histamines. And the movement towards the histamines, it's called positive. Positive means you're moving towards. Chemotaxis. Chemo, we're moving towards a chemical. Taxis, like taxi, taxis take you someplace. The word taxis means movement. So we got movement towards the chemical, movement towards the histamines. And the monocytes and the neutrophils will wiggle out of the blood vessel and go to where the infection is. Great. But what do they do when they get there? What do those blood cells do once they get to the site of infection? Well, let's go through their jobs really fast, the jobs of what each of these things do. We got the macrophages. Go over here so I'm not in the way. The first thing, these are like the tanks of the immune system. They're elite phagocytes, which means phagocyte eats things. Their main job is to eat up to 100 bacteria. So they're going to go into the area, start eating streptococcus bacteria. They can eat up to 100 before they die. They also have a second job. It's not their number one job, but it's their secondary job. They can also be what we call a professional antigen presenting cell. What that means is they'll rip up the bacterium, hold a little piece out, and they're going to go try to find a helper T cell. And if they find the helper T cell, they're going to show it, and they're going to activate all of the adaptive defenses, which we're going to talk about in a couple of days. The helper T cells, they're kind of like the boss of the immune system. So it's like, we're going to go find Mr. Kowalski, because he's the boss of the building. Where are we going to find him? Well, we would find him in the office. The helper T cells offices are lymph nodes. So if you ever had an infection and you've got those little bumps that get swollen on the sides of your neck, those are lymph nodes. Those are the office, like the place where you're going to find helper T cells if you're a macrophage. So job one, eat a bunch of bacteria. Job two, take a little piece and go find a helper T cell. Over here we have a dendritic cell. It's the one that was hanging out in the skin. Its only real job, the thing that it's the best at, is being a professional antigen presenting cell. So it's going to take a piece, it's going to swallow, eat the bacteria, take a little piece of it, and go find a helper T cell. It's better at it than the macrophage. It's its number one job. The neutrophil. Neutrophils are like suicidal warriors. They are a phagocyte. They can eat and destroy the bacterium, but they have two main defenses that are both dangerous to the bacteria, but it's also dangerous to the body. One's called a net. It's called a neutrophil extracellular trap. They generate this kind of cool thing with their DNA. And the second one is they can take molecules and generate dangerous reactive oxygen. It's called like dangerous reaction oxygen reaction series can generate a bunch of free radicals and a bunch of chemicals that are very dangerous and highly reactive. And that can kill bacteria. It can also kill your own cells, and it ends up killing the neutrophil itself. So this is kind of like a little suicide attack is really what it is the neutrophil kind of goes out of control and damages everything in the area. All right, we're just gonna take a look real quick of how this plays out. We're gonna look and see what it looks like when a macrophage eats a bacterium. Well, the first thing that it will do is it's gonna reach out with these little extensions and surround the bacterium. And inside also is a cellular structure called a lysosome. We'll label these things in a second. The lysosome will come over and fuse. It's going to come over and fuse with this vesicle that's starting to form. And the enzymes in the lysosome is filled up with a bunch of enzymes. The enzymes are going to break that bacterium apart into little pieces. That's the main thing this macrophage does. It's just going to swallow hundreds of bacteria. That little vesicle will fuse with the lysosome. The bacterium will get disintegrated, and that's mostly what it does. But if it has to, it'll take a piece and put it on its surface on these little things called MHC2 molecules. And you can think of the MHC2 complex as kind of like a lanyard, and on the end would be an ID. But the ID that the macrophage puts on it is a little piece of the bacterium. Because it's going to go off and try to find a helper T cell and say, hey, look what I found. Look, Mr. Kowalski. All right, so that's the job of the macrophage. The dendritic cell, it basically does the same thing, except that it does not eat a bunch of bacteria. It eats one. It does phagocytosis. A lysosome comes over and fuses. All right, the lysosome breaks apart the bacterium, and then it holds a little piece of the bacterium out, and it's going to go try to find a helper T cell in a lymph node. The last of these is the neutrophil. The neutrophils roll up. They're going to eat the bacterium. A lysosome will come over and fuse, and that'll break it apart, except they're not a professional antigen-presenting cell. They're going to do a couple of things in response to identifying and breaking apart this bacterium. They're both dangerous. The first thing they might do is generate a net, which they use their DNA, and they generate this little extension coming out of itself. It's like a net. It's kind of like a trap. And embedded in those little pieces of DNA are these toxic chemicals that can kill things. What we call this little extension that comes out of the cell is a neutrophilic extracellular trap, NET, it's a net. When bacteria get stuck in it, it kills them. But this little net is also dangerous to your own cells. And what will happen is once the neutrophil dies, macrophages are going to have to come over and they're going to have to eat and remove these. So super dangerous. This structure will kind of kill the neutrophil. It'll also kill the cells around it. Second thing that the neutrophil can do, oh crap, we got an infection. We're gonna have to try to kill as much things as we can. It'll go through what's called oxidative burst, where it generates a bunch of reactive free radical molecules that damage itself and kill it. It also kills cells in the area, and it kills the bacteria. So these things are kind of dangerous, neutrophils. They come in and they start generating problems, and they kind of take out everything in the area, whether it's your own cells, whether it's the bacteria. These two processes will actually kill the neutrophil. So it does do some damage, but they limit their damage by kind of killing themselves, and they don't generate as much tissue damage in your own body as they would otherwise. One more defense to activate. Way back here in this picture, if the monocytes and the neutrophils, they come out here into the skin, they recognize things aren't going so well. There are a lot of invaders who are kind of getting beat. We need some extra help. What they'll do is they will release chemicals called pyrogens. Now, pyro means fire, and a pyromaniac loves to play with fire. Pyrogens, these are chemicals that travel to the brain, and what's going to happen is that the hypothalamus of the brain is going to initiate a fever. The hypothalamus will initiate a fever, and that's going to cause your body temperature to rise. Why? To kind of speed everything up, to get your defenses moving faster, to get your healing moving faster. And it'll also make you feel kind of crappy. You'll get a headache, you won't feel good, you'll want to lay down. So the purpose of a fever is to make you feel like crap, so you lay down and don't burn any energy. And then your body is going to raise your temperature and put all your energy resources into fighting the infection. All right, so just a real quick summary. Neutrophils and monocytes roll along blood vessels in a process called margination, where they stick to the P-selectins. When they find histamines and gaps in the blood vessel, they'll move towards the histamines, positive chemotaxis, and they'll squeeze down and squeeze through the gaps in the capillary in a process called diapedesis. And they end up here in the area where there's the infection. If it's too tough, if it's too dangerous, they'll release pyrogens to activate a fever. What do these 3 cells actually do? Macrophages swallow as many bacteria as they can, up to 100 before they die. They can also be an antigen-presenting cell, where they hold a little piece out and go find a helper T cell. Dendritic cells, all they do is swallow, rip apart a bacterium, hold a piece out, go find a helper T cell. Neutrophils, we're the suicide warriors. When we swallow a bacterium and break them up, and we realize things are getting pretty bad around here, they can do one of 2 pretty significant defense mechanisms that aren't just dangerous to the bacteria, but they're also dangerous to you. One's called a net, neutrophilic extracellular trap. The other one's called oxidative burst. They generate a bunch of dangerous chemicals that don't just kill bacteria, they kill themselves. They also kill other cells in the area. Folks, I hope this helps. Hope to see you soon.